Today I'm going to look at homework I have previously assigned in Chapter 6 of Physical Chemistry. So problems 1, 4, 6, 7, 17, 20, 22, 29, and 34. Start by looking and reading the various problems. Problem 1. Calculate the Helmholtz energy of reaction and the Gibbs energy of reaction, the standard energy of reactions for the combustion of benzene. At 298 Kelvin. From the combustion of using the combustion of enthalpy of benzene and the entropies of the reactants products. So, for number 1, we're told we can directly use the enthalpy of combustion rather than calculating it from the heats of formation. However, we're asked to calculate the entropy of combustion prior to finding either Gibbs or Helmholtz energy. So to calculate the enthalpy of combustion, we do the products minus reactants raised to the power of the coefficients, because our equation is, remember, equals the sum of our nu sub I S sub F. So what that means is we have 213.8 times 6. We have 70.0 times 3 minus 173.4 times 1 and minus 205.2 times 15 over 2. We punch those into the calculator. What we should get is something like negative 219.6 joules per mole Kelvin of reaction. Our value for delta H of combustion is just negative 3268 kilojoules per mole of reaction. Now to calculate our Gibbs, that is the easiest thing. Gibbs is simply our delta H minus T delta S. So plugging that in, negative 3268 kilojoules per mole minus 298.15 Kelvin times our negative 219.6 joules per mole Kelvin. However, we have to watch out our units, watch for our units. So times there is 1 kilojoule, there's 1,000 joules. That will give us our Gibbs. Gibbs being 3268. 219 divided by 1,000. Okay. We'd have our Gibbs free energy for this reaction as negative 3202. We'll say round at 3203 kilojoules. 203 kilojoules. Okay. To get Helmholtz is a little bit harder, but Helmholtz, remember, is our internal energy minus T delta S. The problem is, how do we get internal energy? We have our enthalpy values, but remember that enthalpy is equal to internal energy plus PV. And while we don't have pressure or volume, we can say PV is equal to delta nRT plus delta nRT. Watching out for our units. So the important thing to note is how many gas molecules do we have in this equation? Well, water is a liquid. Benzene is a liquid. So what we have is 6 moles of CO2 come from 15 halves moles of of oxygen. So 6 minus 15 halves leaves us with the delta N is negative 1.5. R is just our 8.314, and temperature is 298.15 Kelvin. So we can simply take our Gibbs, and Gibbs minus 1.5 times moles, 8.314 joules per mole Kelvin times 298.15 Kelvin. And of course, you have to always turn this into the correct units, 1,000 joules and 1 kilojoules, so that we don't blow our numbers out of the water. So the effect is we are changing it by negative 3.7 kilojoules. So 320. No, that's right. It'd be Gibbs minus NRT. Minus NRT. So you'd be adding 3.7 kilojoules. 2. So you'd get something like negative 3,199 kilojoules. Problem 4. Consider the equilibrium expression NO2 goes to NO and 1/2 molecule of oxygen. If 1 mole of NO2 is placed in a vessel and allowed to come to equilibrium at a total pressure of 1 bar, an analysis of the contents of the vessel give the following results. At 700 Kelvin, the fraction, the pressure percentages from NO to NO2 is 0.872, and at 800, it's 2.5. So first thing is to calculate the Kp at 700 and 800 Kelvin, and then calculate the Gibbs standard for this reaction and the enthalpy standard of this reaction at 298 using only the data from this problem, assuming that the enthalpy standard for this reaction is independent of temperature. And then finally, calculate your Gibbs standard for this reaction and enthalpy standard for this reaction using the data tables, and compare your answers to the part with part B. So on number 4, we have a K expression. K is O2 to the 1/2 times NO over NO2 based on this chemical equation. And we're given the relationship of NO and NO2 to each other at various temperatures, knowing that we start with 1 mole of NO2. Well, how do we do this? Because we're not given the amount of O2, otherwise we could plug those directly into the K expression. However, we do have everything we need to know to find out all the relative values, because we can set up an ice table. At an initial point, NO2 is 1 mole. At an initial point, the products are 0 moles. And then at conclusion, we lost X and we gained X and a half X. So at equilibrium, we can say that NO2 is 1 minus X, NO is X, and O2 is 1/2 X. Well, at these relationships are essentially x over 1 minus x. So if that is equal to 0.872, we can find out what is our x. So we cross multiply to get 0.872 minus 0.872x equals x. So when we add them to one side, you get 0.872 equals 1.872, giving us our x value. X value being 872. X is 0.46, we'll say 58. Doing that again for the other situation, where it's 2.5, you'd get situation 2.5 minus 2.5x equals x. So you'd get 2.5 equals 3.5x, x being, in that case, something like x equals 0.7143. In this case, we need to calculate our total moles before we calculate this, because right now, moles, we can only do a mole fraction, K sub x. But to get mole fraction into K sub p, we're going to need to take one more step. So what we're actually calculating here is K sub chi. K sub chi is going to be our chi of O2, 1/2, times chi of NO over chi of NO2. But we have to multiply by P over P naught to the negative, to essentially our delta, negative delta V. However, we're told that the total pressure is 1 bar. 1 bar. So 1 bar over 1, this whole term cancels out. So we can literally say K sub chi is equal to K sub p, as long as we calculate the relative mole fractions. So to do the relative mole fractions, we need how many total moles we have. So if x is 0.4658, the total moles would be at moles total going to be 0.4658 plus 0.4658 divided by 2 plus 1 minus 0.4658, which will give us 1.2329, meaning that our K sub p is going to be 0.4658 divided by 2 times 1.2329 to the half. 0.4658 divided by 1.2329 over 1 minus 0.4658, 1.2329. So our Kp at 700 ends up being something like 0.3790. Doing the same thing at 800. 800. So following the same work, 0.7143 divided by half plus 0.7143 plus 1 minus 0.7143. Our total moles are 1.3572. So N total. So our Kp at 800, is going to be, essentially it becomes, let's see, 1/4 x chi to the 3/2 over n total to the 1/2 all over 1 minus x, 1 over chi. Actually, 1 over, sorry, not 1 over half, 1 over the square root 2. So, 0.7143 root 3 over 2 divided by square root of 2 divided by mole total 1.3572 root 0.5, finally divided by 1 minus 0.7143. You get the Kp at 800 to be 1.2825. So we've answered A. What is our Kp's at your relative under these relative situations? Now, moving on to part B. For B, we can simply do this. Delta G equals negative RT ln K sub P. Don't overlook the easiest possible thing. We can always find our Gibbs at a temperature using this. So remember our K sub P at 700 is 0.3790. And our K sub P at 800 is 1.2825. So the other equation we'll need for this is that the integral from T1 to T2 is going to be ln Kp dln Kp and equals 1 over 8 delta H over R integral of T2 to T1 of 1 over T squared dt. So basically, we can find, using the two ln Kp's, we can find our delta H. And then, using our delta G at a T2, we can find our delta G of T1. T2, delta G at T1 over T1 plus delta H 1 over T2 minus 1 over T1. So, step 1, let's go ahead and find our delta H using our two temperatures. First thing is to find our ln K sub P. First thing is to find our ln K sub P, the change in the K sub P's ln of 1.2825 minus the ln of 0.3790 gives you 1.2190, and converting this into kilojoules at say negative 1 over 1 over 800 minus 1 over 700, making that negative, divided by R, and converting this into joules, you get equal to negative, well, actually, sorry, positive 0.02148 delta H. So solving for delta H, we have delta H being 1.2190 divided by 0.021478. You'd get something like 56 kilojoules, 56.75, 75, we'll say 6 kilojoules. 56.756 kilojoules for the enthalpy. Now we need a single Gibbs value at a temperature. It doesn't matter whether we choose 700 or 800. We could do this just fine. Delta G at, we'll just say 700 is equal to negative 8.314 by 1,000 to get this into kilojoules times 700 Kelvin times ln of 0.3790. So ln 0.3790 times 700 times 8.314 makes this a positive 5.646 5.646 kilojoules. Now, using the fact that we have two temperatures and two temperatures and one we can two temperatures and one Gibbs and a delta H, we can say Gibbs at 298 is equal to 298.15 times our 5.646 over 700 plus our, we said our delta H is 56.756. Then 1 over 298.15 minus 1 over 700. If we do that, we should get a enthalpy value of a Gibbs value of approximately Gibbs value of approximately, say, 34.998 kilojoules at 298. Now, for the last part, part C. Part C, it just asks us to calculate and compare otherwise. So for this, the delta H values of NO need to be known. Delta H and delta G. Delta H and delta G, so of NO2 and NO and a half mole oxygen. Oxygen is going to be 0 in both cases. So 33.2, 91.3, 51.3, and 87.6. So at 298, you're just going to say, well, 91.3 minus 33.2. What's our enthalpy? Positive 58.1. Relatively close to our 56.76. Or 56.8. Add our Gibbs at 298. It's going to be what? Like 87.6 minus 51.3 or 36.3. So, but 1.3 kilojoules off for Gibbs, about maybe another 1.31 kilojoules off for enthalpy. So not too bad. Not too bad all in all. Problem 6. Consider the equilibrium expression of ethane goes to ethene and hydrogen gas at 1,000 Kelvin and a constant total pressure of 1 bar. Ethane is introduced into the reaction vessel. The total pressure is held constant at 1 bar, and at equilibrium, the composition of mixture in mole percentages are 26%, 26 of hydrogen, 26% ethene, and 48% ethane. Calculate your Kp at 1,000 Kelvin. And if enthalpy of this reaction is 137 kilojoules, calculate the Kp at 298. And then calculate your Gibbs standard reaction for this reaction at 298.15. Okay, this one is far simpler. Number 6, we have ethane breaks apart into ethene and hydrogen gas at 1,000 Kelvin and 1 bar pressure, which is important. And it gives us, here's the mole percent of each guy. The mole percent is essentially a mole fraction of, it's essentially how many moles over the total moles. So we don't have to do too much. So they ask us first to calculate Kp. Well, Kp is going to be equal to K chi P over P naught of delta V, a delta nu. However, since pressure is 1 bar, this whole term cancels out and Kp is equal to K chi. So we can say 0.26% squared over 0.48 will give us our Kp at 1,000, which is 0.14083. Easy enough. Part B asks us to calculate what's Kp at 298 if the temperature, if the enthalpy is 137. So we have ln Kp at 298 minus ln Kp at 1,000 equals our delta H over R, 1 over negative times negative 1 over 298.15 minus 1 over 1,000. Okay. Key thing is to watch out for the units. So ln Kp, we don't know that, but we do know ln Kp at 1,000, 0.414083. So ln Kp at 298 minus so plus 1.96, we'll say 02 equals, so if our negative, we'll say 130, let's evaluate we have 137 over 137,000 joules divided by 8.314 times 1 over 298.15 minus 1 over 1,000. So that's going to be something like negative 38.7900. When I subtract my 1 point, I subtract my 1.9602 to both sides, You get ln K sub P is going to be equal to negative 40.7502. And then we have to do the inverse log. So inverse log to get rid of the ln, you would have something like your K sub P at 298 is something like 2.006 times 10 to the negative 18th. So that calculates your K sub P. Lastly, with our K sub P at 298, what's our delta G? Once again, delta G can just be negative RT ln K sub P. So negative 8.314 times 298.15 ln 2.006 times 10 to the negative 18th. Doing that gives me my value. 5 times 8.314, make it negative, divided by 1,000. You get positive 101.01 kilojoules. So, easy enough. Problem 7. The pressure dependence of Gibbs free energy of G is quite different for gases and condensed phases. Calculate the molar Gibbs enthalpy. The molar Gibbs the molar Gibbs energy for the process of carbon solid graphite at 1 bar 298.15 Kelvin being heated and pressurized to 325 bars at 298.15 Kelvin. And helium at 1 as a gas 1 bar going to helium pressurized to 325 bars. And that answering the question, by what factor is the molar Gibbs enthalpy greater for helium than it is for graphite? Okay, so number 7 asks us to calculate how the molar Gibbs enthalpy energy changes with carbon versus helium when you increase the pressure from 1 bar to 325. Well, with carbon, you must treat it like a real thing and find what is the volume of this if you have 1 mole. 1 mole. So to calculate volume, you're going to say volume equals density over, let's see, mass over density. And so it's going to be something like 0.0120 kilograms per 1 mole, and there's 1 mole of it. And the density of graphite happens to be 2 to 50 kilograms per meter cubed. So our density being 0.0120 divided by 250 would say our volume is something like 0.00023 meters cubed. Our pressure has gone from 325 bar from 1 bar to 325. So multiply that by 324, which you get something that sounds like 0.001728 bar meter cubed. And then we can turn that into a joule. Now there is, if you do bar meter cubed, something like so we have to turn this into 1 joule. You want Pascal per meter cubed is equal to 1 joule, and there's 10 to the 5th pascals per 1 bar, and then the 1 joule per bar Pascal meter cubed. So what you get is something like an increase in 172.8 joules to compress graphite. Now, helium is much easier to consider because we can treat it like an ideal gas. So when you integrate this, you get something like 1 mole times 8.314 joules per mole Kelvin times 298.15 ln 325 bar over 1 bar. The bar over bar cancel out, and you get 314 times 5 ln divided by, and you get something like 14337 joules. So a lot different. If you divide by the two numbers, 14337 divided by 172.8, you get that it's approximately 83 times greater. Approximately 83 times greater to Gibbs James and Gibbs molar energy to pressurize a gas than is to pressurize carbon. So, okay, looking at problem number 17. Calculate the chemical potential of mixing for oxygen at 298.15 in 1 bar in air, assuming that the mole fraction of oxygen in air is 0.210. Use the conventional Gibbs molar energy defined in section 6.17. Number 17 asks us to calculate the chemical potential of a mixture of oxygen and air, assuming that the mole fraction of oxygen is 0.210. Well, to calculate the chemical potential of a mixture, you can take the chemical potential of pure oxygen plus RT ln of the mole fraction. Now, while chemical potential of a mixture is a little bit harder to calculate, we can say that is equal to the molar Gibbs energy without the change. However, we're able to say that is approximately equal to the negative T of the Gibbs molar entropy. And that is known for oxygen. That is known to be 205.2. So we can say the chemical potential pure is simply put negative 298.15 times 205.2. And that leads us to a chemical pure potential of negative 61180 joules. Now, 61180 plus our 8.314 times our 298.15 natural log of oxygen of 0.210, and you would get the chemical potential of the mixture to be negative 65048.9 joules per mole of oxygen. Chemical potential of that mixture. So all in all, that one was relatively straightforward. Problem 20. Calculate the Gibbs free energy for isothermal expansion of 2.25 moles of ideal gas at 325 Kelvin from an initial pressure of 12 bar to a final pressure of 2.5 bar. Number 20 has us calculating the change in Gibbs for isothermal expansion from 12 bar to 2.5 bar. So that can be summed up by Gibbs is equal to the integral of nRT over P dP. That tells you to have nRT ln P2 over P1. Given the fact it's 2.25 moles, 8.314, and 325 Kelvin, then it's just a matter of ln of 2.5 over 12. Plugging that in and evaluating, what you will get is negative 9536.6 joules as our answer. Problem 22. A sample containing 2.5 moles of helium, 350 Kelvin, is mixed with 1.75 moles of neon at 350 Kelvin and 1.50 moles of argon at 350 Kelvin. Calculate the Gibbs free energy of mixing and the entropy of mixing. Okay, number 22 asks us to calculate the entropy of mixing and the Gibbs of mixing, the free energy of mixing for three gases: 2.5 moles of helium, 1.75 moles of neon, and 1.5 moles of argon at 350 Kelvin. The first step is to find the total moles and the mole fraction of each. So the total moles is a matter of just summing up our three values. Sum up 2.5, 1.5, and 1.75, and we should get the total moles to be 5.75. From that, we can easily get the mole fraction. Mole fraction being moles over total moles. So the mole fraction of helium becomes 0.4348. The mole fraction of neon to be 0.3043. And the mole fraction of argon to be 0.2609. Now, the only difference between Gibbs mixing and entropy of mixing is the temperature. So, say 5.75 times R times T. So, to get our Gibbs mixing. So, here's the only difference is we have to do the sum. The only thing we have to do is we have to do the sum. So, 0.4348 ln 4348 plus 0.3043 ln 3043 plus 0.2609 ln 2609. Oh, and the entropy of mixing is also negative. That's the only two differences, really. So the sum, doing the sum real quick, 0.4348 ln 4348 plus 0.3043 ln 3043 plus 2609 ln 0.2609. That sum, all that sum comes down to 1.0747. Take that, multiply by your temperature, multiply by your R, multiply by your moles, 5.75, your Gibbs mixing, delta G mix, becomes negative 17982 joules, or essentially almost 18 kilojoules. Now, entropy of mixing, we're just going to take the Gibbs and divide by negative 350. You divide by negative 350, your entropy of mixing simply becomes positive 51.38. We'll say 378 joules per Kelvin. So, pretty easy, all things said and done. Problem 29. assuming the enthalpy of formation, enthalpy standard formation, is constant over the interval from 275 Kelvin to 600 Kelvin, calculate the standard Gibbs free energy for the process where water gas is heated from 298 Kelvin to 600 Kelvin. Calculate the relative change in the Gibbs energy. So, number 29 asks us to calculate the how much entropy would change if you were to go from 298 to 600 Kelvin. Now, how much Gibbs free energy would change if you went from 298 to 600 Kelvin for steam? So for this value, you need the enthalpy of formation of steam, and you need the Gibbs formation of steam at 298. After that, it's simply a matter of utilizing the equation that says our Gibbs at our desired temperature, 600 Kelvin, is going to be equal to 600 times our Gibbs at our standard temperature, 228.6, divided by 298. Then add our enthalpy, negative 241.8, 1 over 600 minus 1 over 298. So you do that. Plug this in. Let's get the right term, negative 241.8 times 1 over 600 minus 1 over 298. That term is 0.4084. We'll say 1. And then we have negative 228.6 divided by 298. That's negative 0.7671. So we add those two terms together. 40841. And then multiply by 600. 600, and you get the Gibbs free energy is now 215.22 kilojoules. Now, the other thing they ask us to do for that one is calculate the relative change. How much has it changed over that temperature range? So to do that, you're going to take your current one minus your original one, 28.6, and then we can divide by our original one. And what you get is something, and then times by 100 to get percent change. So it's dropped by 5.8%. Not a huge drop, but we are dealing with engineering situations. So, and finally, for number 34, you have a container of pure oxygen and nitrogen, 298 Kelvin and 1 atmosphere pressure. Calculate the Gibbs mixing relative to the unmixed gases of a mixture of 10 mole of oxygen and 10 mole of nitrogen, a mixture of 10 mole of oxygen and 20 mole of nitrogen, and then calculate the Gibbs mixing of 10 mole of pure nitrogen added to a mixture of 10 mole of oxygen and 10 mole of nitrogen together. Last problem, number 34. We're looking at three situations. The Gibbs mixing of pure oxygen, 10 moles of pure oxygen with 10 moles of nitrogen. Gibbs mixing of 10 moles of oxygen with 20 moles of nitrogen. And then what would happen if you have the first situation mixed and you add in another 10 moles of nitrogen to give us the second situation? So what is the additional mixing? So the first situation, we have 20 moles of total gas mixing together. So times 8.314. And we're going at, what's the temperature? I think at 298. 98. So our mole fraction. So our sum, 10 over 20. 10 over 20. So 1/2 ln 1/2 plus 1/2 ln 1/2. We do that. Our Gibbs mixing for our first situation is simply negative 3. Negative 34346.4 joules. Now, our second situation. We have 30 moles total. So it's changed a little. 8314 times 298. And so now our first gas is 1 over 3 ln 1 over 3, 10 over 30. The other one is 2 over 3 ln 2 over 3. Calculate that, and would get the Gibbs is increased a little bit to 47310.3 joules. The third situation is a little bit harder to do because you cannot treat it as 3 separate gases, because the nitrogen mixing with nitrogen does not see an increase in Gibbs mixing because of them both being nitrogens. So, but if you can't treat it as 3 separate gases, how would you treat it where we mix an additional gas into already mixed gases? You can't treat the oxygen and nitrogen as one gas mixture because they are not separate. Because when nitrogen mixes with nitrogen, there's no increase. Fortunately, we have the fact that Gibbs is a state function to help us. So Gibbs of situation 3 is actually going to be Gibbs of situation 2 minus Gibbs of situation 1. Because we're going from the end of situation 1 to the end of situation 2. So when we have already mixed gases and we mix in that second set of gas. So with that in mind, you get negative 47310.3 minus the negative 34346.4, and your Gibbs for that third situation is 12,964 joules. That would be how you approach that. So thank you for your time, and good luck. Keep working these problems.